These are notes for 4.4 and 4.5 for the second day of homework on these two sections. So essentially 4.4 and 4.5 are pretty much the same in terms of developing a function based on one variable, just like we did yesterday. The extension would be now maximizing or minimizing by, after we get the function, doing x equals negative b over 2a. So that being said, I'm going to work through number one here all the way through in terms of creating the function and also doing negative b over 2a to minimize or maximize, even though this problem doesn't say it. And then example 2, we're just going to set up as it's generalized with a wire length of L instead of 4 meters, for instance. Then algebra gets extremely nasty as you get to trying to get the function into standard form of a quadratic, which we're not going to have to do. So that being said, we'll get through example 1, 2, and then I'll quickly do example 3, as we'll see that will go fairly quickly. Okay, so if we have a piece of wire that's 4 meters long, let's just go ahead and simply start out by drawing a wire diagram. It's 4 meters long and is cut into 2 pieces. Each piece is bent into a square. Now, what's interesting about this is we don't know what size or where the wire is being cut. So we're just going to make this one x, and if the whole segment is 4 and the one segment is x, then the other segment is 4 minus x. So this is being bent into a square, which means the perimeter is x, which means the side is x over 4. This same, this would be 4 minus x divided by 4. And then each piece is bent, or combined area of the two squares. So now we want area of both of the figures added together. Since both of them are in terms of x, there's not any sort of substitution that's necessary. So I'm going to just write out the area total. You don't have to write this out, but there's just a nice model area, a nice model to know what we're overall trying to create. Area square 1, area square 2. So we're going to make this a of x because the area of the overall would be the addition of 2. First area is x over 4, and note it's the area of a square, which is side squared. So that'd be x over 4 squared plus, here we have 4 minus x over 4 squared. And now what we're going to do is distribute all this out, combine like terms, and we're going to get a quadratic. And for the 4 or 5 section with any of your problems, what you're going to do is maximize or minimize it. So we're going to actually do that on this problem. We won't, as I said, on the next one. So if I square that, we get x squared over 16 plus, here in the denominator we have 4 squared, which is 16. In the numerator, that'd be 4 minus x times 4 minus x, which is 16 minus 8x plus x squared. And we can break that up into individual terms and combine like terms. So if you look right here, we have a 1x squared. This would also be a 1x squared. Note, break it up into 3 terms. So that'd be 16 over 16, which is 1. In fact, let's go and put it in standard form. I'm going to put the constant last plus 1. And the x term in the middle here is negative 8 over 16, which is just negative a half. And let's write it like this, negative a half x. And then we have the 1 over 16 plus 1 over 16, which gives us 2 over 16, which then reduces to 1/8 x squared. Now we want to, since the a value is positive, that means the parabola is facing up, which means the minimum value, the vertex would be the minimum value. So we want to do negative b over 2a b is negative a half, a is 1/8, And if we simplify that, we have the 1/2 on top. Sorry, I'm running out of room. And then 2/8 on the bottom, which is 1/4. Multiply by the reciprocal of 1/4, which would be 4. So 4 times 1/2 would give us 2. So the x value of 2 is what will minimize the area, which is interesting. That would be cutting it directly in half. And then we can get the area by taking 2 and substituting it in. And we could also, I suppose, get the perimeter as well. So just for some more practice, again, we're not going to do the minimum value part or maximum. I believe this is minimum as well. It should be. We're just going to work on some algebra here, what this looks like in more generalized form. So we have a wire. Its L overall is cut into 2 pieces. So we have x here, L minus x. Of course, you reduce that or turn those around, doesn't matter. So the first piece is bent into a square. And the second piece bent into an equilateral triangle. I'm going to decide to do it this way because it's actually opposite of how I have it in the notes, so you can see both of them. I'm going to bend this one into a square and this one into a triangle. Again, I'm doing it in that order because I have it opposite in the notes, and then that just gives you another example to look at some of the simplification of all this algebra. So the side of this, since the whole perimeter is x, side of that would be x over 3. If this is a perimeter of L minus x, then the side would be L minus x over 4, and of course we need the side because then we can substitute it in the formula. So note, area of an equilateral triangle is side squared root 3 over 4, if you recall that from geometry. It's going to be an important formula to remember. Area of a square, for instance, is fairly easy to remember, and others. But area of an equilateral triangle is a little more complex and less well known. It can easily be proven by dropping an altitude to one of the sides, 30, 60, 90 triangle, and then using your 30, 60, 90 triangle and plugged into 1/2 base times height. It ends up resulting in side squared root 3 over 4. We can do that in class perhaps. So if I want to find the area of the overall figure, it'd be area of the equilateral triangle. I'm just going to put a triangle there for this time, and then area of the square. So a of x equals the side squared, which is x over 3, side squared root 3 over 4, plus the area of the square, which would be L minus x over 4 squared. We're only going to go as far as simplify each term. We're not going to combine like terms, which is a little nasty. The other method, where you have the flipping of the x and the L minus x, the algebra definitely gets nasty, and you can look at that in the notes. But in any case, here we go. We have x squared in the numerator, so I'm just going to put it like this, and then we have a root 3. Now that 3 squared right here, 3 squared is 9, but then we can move it down here. Reason being, you can think of this as root 3 over 4, and this is x squared over 9. It's really this multiplied by this, so this ends up going to the denominator. If you want more explanation as to why that is, I can talk in class about that. So it'd be 9 times 4 is 36 in our denominator, plus, I'm going to do the same as I did above, 16. Then we have L squared. And note this is based on x, a function based on x, and L is just a unknown length, but it's not a varying length, right? It's just this is the length of the wire, and we select the length of the wire, but we can vary x after we select the length of the wire in terms of where to cut it. Middle terms would be negative XL or negative LX, and there's 2 of them. I'm going to go negative 2lx and then x squared. Combining your like terms, if we wanted to, we're just going to break that fraction up. If we wanted to combine like terms, we have to get like denominators between these two, and then we'd have to factor out the x squared. Be a little nasty, not as nasty as you'll see in the notes if we flip the equilateral triangle in the square originally. But in any case, here we are. Break it up, L squared over 16, that's your constant term. Minus, you have a 2 over 16, which reduces to 1 over 8. So that's an Lx over 8 plus x squared over 16. One last problem, just to get a little more practice in terms of the setup. The following figure shows two concentric circles, meaning circles with the same center. Radius of lowercase r and uppercase r. Let A denote the area of the outside smaller circle. So if you recall, say if we have a circle here, I guess I'll do it with a highlighter. So let's say if we have a circle, we want to find the area of the outside part of it, not including the inside. So now if we have this circle and we subtract the inside of it, we see we get the area of that kind of like donut figure, which is the large area minus the small area. So that's what we're going to do. There's a large circle minus the small circle. So area overall is area of the large circle, which I'm going to denote by the uppercase r, because that's the radius of the larger circle, minus the area of the smaller one. So what would that be? So we want to get this in terms of x, which is interesting, segment that goes from a tangent to the inside circle. Well, let's see what happens here. Well, what's the relation? First off, we can set up the problem right here. It'd be area equals, pi uppercase r squared minus pi r squared lowercase r squared. So what's the relationship here? Well, let's see. If I draw my radius to there and then my radius to there, we now have a right triangle right here. As we know, point of tangency creates a right angle. So that's uppercase r and that's lowercase r. And now we can create Pythagorean theorem from that. This is our second equation. Like we talked about getting two equations. R squared plus x squared equals uppercase r squared. So I look over there and I go, that looks interesting. If I come back over to here, look at what happens if we factor out the pi. We have an r squared minus r squared. Look over here, if I solve for x squared, I'm just like looking for patterns in the number. Try to get, so you're gonna be a little more creative here. Figure out how to get this in terms of x. Well, what's interesting is I get an r squared, so here's the logic other than just trying things. If I have an r squared minus an r squared in this equation right here, you go, well, if I can get that in this equation in terms of x in some capacity, I can substitute in for this rather than for like y. So that's what I did. I saw these pi's in common, or in common between those two terms, factor them out. I get r squared minus r squared. Come over here, get r squared minus r squared by itself, and that equals x squared. So we can insert x squared right there. And now we have the area of the outer rim just based on x, which is super simple, nice formula for the area of that figure.